Hello everybody, welcome back to Physics 425. What we were talking about in the last video was some of the properties of liquid helium-4, and in particular the fact that if we use a model of non-interacting bosons, so energy is h bar squared k squared over 2m, then we're not able to reproduce some of the measured thermodynamic quantities for liquid helium. And it was Landau who proposed a different energy dependence or dispersion relation for excitations out of the condensate. And so if you recall, a long time ago, we set the ground state of our system of bosons to have an energy E equals 0. And so here, what we've plotted is energy as a function of K, and so all of these energies above 0 represent helium atoms that have been excited out of the ground state or out of the Bose-Einstein condensate. So if you were thinking in terms of a two-fluid model, all these particles in excited states would represent the normal fluid component, and all of the remaining particles left in the condensate would represent the superfluid fraction. So last time we looked at the linear part of this dispersion relation, which we called the phonon contribution. And so in this case, the energy is proportional to K. And we were able to use the grand potential for a system of bosons and insert the right K dependence for epsilon, and then go ahead and calculate entropy by taking a derivative of this grand potential and then finding the heat capacity from that entropy. And what we found was that the phonon contribution to the heat capacity of liquid helium-3 had a temperature cubed dependence. And so before we go and look at some of the experimental data again, I want to just briefly talk about why this is called the phonon contribution. So if you were to think of sound, you would have a relationship where the speed of sound would be equal to the frequency of the pressure wave times its wavelength. And so this could be rearranged where F would be equal to V times 1 over lambda. And if we wanted to, we could multiply both sides by 2 pi, and so we would have omega is equal to V times 2 pi over lambda, which is the wave number K. And so finally, multiplying by h bar omega would be the energy, and that would be equal to V times h bar K. And so if you compare this to what we wrote down for the phonon dispersion relation, we've written that epsilon phonon is equal to this U1 h bar K. And so this has a similar type of relationship, or an identical relationship to what you'd expect for sound waves. And so in fact, what U1 represents is a speed of sound in liquid helium. And so this is the reason why we call this linear part of the excitation spectrum in liquid helium the phonon contribution. Okay, and so if we go and look at some of the experimental data, this is a measurement of the specific heat as a function of temperature on a log-log scale. And the dashed line is a specific heat that's proportional to T cubed, and so that's what we calculated from the phonon contribution. And what you find is that at temperatures below about, this 0.2, 0.3, 0.4, 0.5, that's about 0.6 Kelvin. So below about 0.6 Kelvin, our calculation does a very nice job of reproducing the experimental data. But above this temperature of about 0.6 Kelvin, we see quite large deviations, especially considering that this is a log scale, between the phonon contribution to this specific heat and the experimentally measured specific heat. If we look at this on a linear scale, you can see our 0.6 Kelvin, oh sorry, that's not quite right, our 0.6 Kelvin is somewhere around here, and so that's where we do a nice job of reproducing the experimental data, and then above that you can see the difference is very, very large. And what we're going to do today is we're going to try to take into account the Roton part of the excitation spectrum and see if we can do a calculation there and see if we can come up with a calculation that is closer to the experimental heat capacity. And so let me just draw this curve again. So this is the helium, or let's say superfluid helium. So superfluid helium for dispersion relation. And so this is excited energy states, and here's K, and so we have this linear part, then it goes through a maximum, and then there's some kind of minimum. We're going to be interested in the minimum today. So here is the phonon part, and here's what we're going to call the Roton part. And so this Roton part is characterized by a minimum positioned at K0, and the height of the minimum occurs at delta. And if we were to write down this dispersion relation, it's delta plus, and then we could parameterize it in the following way: K minus K0 squared times a constant. And so the constant we're going to write as h bar squared over 2m. And so our adjustable parameters in this model of the Roton part of the dispersion relation is our delta, K0, and some kind of effective mass, capital M. The motivation for this is that if we were at really low temperatures, then because the Roton part of the spectrum has to get to an energy delta before those states are occupied, at very low temperatures, there's insufficient energy to occupy those states. And in that case, the phonon part of the dispersion dominates, and then we get that T cubed specific heat, which matches the data at the very low temperatures. But once you have enough thermal energy to start occupying the Roton states, then there's going to be an additional contribution to this heat capacity, and we're going to try to see if we can do that calculation and show that above about 0.6 Kelvin, then this contribution starts to account for the differences that we so far have seen between the experimental data and the phonon contribution to the specific heat. So at the lowest temperatures, the thermal energy, say kBT, is less than delta, and it's inadequate to excite helium-4 atoms out of the condensate and into Roton states. However, once we cross this threshold where kBT becomes comparable or bigger than delta, we do start to occupy these states. So once we cross a threshold temperature, we start to occupy Roton states. And we get another contribution to CV. So if we look at that, if we look back here, that's kind of what we need. We need something that works well up to some threshold temperature around here, and then above that we need something else to be activated, and that's what the Roton states are going to do. Okay, and so our approach is going to be the same. We're going to write down the dispersion relation, and then we're going to try to plug that into our grand potential, our low temperature approximation for the grand potential, and then just calculate away. So Rotons. What we're going to do is we're going to say the Roton energy spectrum is given by these parameters delta, K0, and M. And so at the lowest temperatures, our grand potential is V over 2 pi squared kBt integral from 0 to infinity k squared ln of 1 minus, and so in this exponential what we had was epsilon of k, and so we'll put in our actual spectrum now. So we're going to have one factor that's going to be minus delta over kBt. So it was minus epsilon over kBt, and so we get first a minus delta over kBt, and then because we have two terms in epsilon r, we can write that as a product of exponentials, and it's going to be minus h bar squared k minus k0 squared over 2m kBt, and that's all integrated with respect to dk. Okay, so we're going to start right away making some approximations. And so the first thing we're going to say is that Rotons are only present, those states only exist at high energy. Right? At least compared to the phonon contribution, which goes all the way down to 0 energy, we have to cross this threshold delta. And for the temperature range that we're talking about, we'll say that delta is a pretty high energy compared to kBt. And so that means that this e to the delta over kBt is in general going to be small. And so what we have is ln of 1 minus some small prefactor, e to the minus delta over kBt, times some other stuff. And if that prefactor is small enough, then we can approximate the ln of 1 minus a small number as being just minus the small number. And so we will have eliminated the ln from inside of our integral. And so that's our first approximation. Okay, with that then, this grand potential for the Roton states is approximately, we have an overall minus sign now, v over 2 pi squared kBt e. We'll take the minus delta kBt outside the integral because the integral is over wave number k, and there's no k in minus delta. And so we have k squared e to the minus h bar squared k minus k0 squared over 2m kBt and dk. Okay, so next we'll make some substitutions, and so we'll define x squared as being the factor inside the exponential of the integral. So it's h bar squared k minus k0 squared over 2m kBt. And so just, let's see, I think it's going to be useful to write k minus k0 as 2m kBt over h bar squared. We'd have to take the square root and then multiply by x. Okay. And so I'm going to define the square root thing to save us a bit of writing as 1 over lambda. Okay, So one thing we'll have to make note of is that when k is equal to 0, x is going to be equal to minus k0 times lambda, or minus lambda k0, right? So if we put k equals 0 here and solve for x, we get minus k0 times lambda. All right, and then if we set k equal to infinity, then let's see, x will also be infinity. Okay, so that's going to be our change of variables. And so let's see, what else do we have? We have, sorry, if I solve for k, I want to take the differential. I want to know what dk is. So k is equal to x over lambda plus k0, and so that means dk, if k0 is just a constant, dk is going to be dx over lambda. Okay, so I think we have everything we need to make our substitution. So we're going to replace dk with this thing. Inside this exponential, we're going to have an x squared, and then we're going to have to be careful about k squared here. We're going to have to replace it with x over lambda plus k0 all squared. And so let's do all of that. So our grand potential for Rotons then is minus v over 2 pi squared kBt. Nothing happens there. We have e to the minus delta over kBt. And then we had the integral from 0 to infinity over k. We said our 0 limit is going to be minus lambda k0, and our upper limit is going to stay at infinity. Then we had k squared, which we're going to have to write as x over lambda plus k0 squared. Then we had the exponential, where everything in the exponential was defined as x squared. And then dk becomes dx over lambda, and so I'm going to put that 1 over lambda out here. Okay, so minus v over 2 pi squared kBt e to the minus delta over kBt. I'm going to factor out the lambda squared, that's the 1 over lambda that's inside the square, and so we'll end up with a 1 over lambda cubed here, and we have the integral of minus lambda k0 to the infinity, and we factored out that lambda, so we get x plus lambda k0 squared e to the minus x squared dx. All right, one thing that I want to point out is that when we looked at the experimental specific heat of liquid helium, above about 0.6, it increased rapidly. It increased exponentially. And so we can already start to see some of that exponential dependence emerging from our grand potential. And so we can already see the exponential t dependence emerging. It's not a straightforward exponential, like it's e to the minus 1 over t. However, if you have, say, a large t, then you'd get e to the minus 0, it's about 1. If you go to low t, it would be e to the minus a really big negative number, and so it becomes very small. And so it still has the feature that this exponential gets larger and larger as t increases. Okay, so so far we've made only one approximation, and that was approximating the ln of 1 minus a small number as being minus a small number. We're about to do a second approximation. So in this expression, if it was true that lambda k0, which is the lower limit or is in the lower limit of our integration, if that was a large number, which it is, and I think we'll try to confirm that maybe near the end of the video. So if that was a large number, then the e to the minus x squared would be very small when x was less than or equal to lambda over k0. In other words, if we were to plot the argument of this integral as a function of x from x equals minus infinity to minus lambda over k0, we would find very little area underneath that curve. And so what the approximation is going to be is we're going to replace the minus lambda over k0 by minus infinity. And that's going to be useful because then we'll be able to analytically evaluate this integral. Okay, so in other words, or that is, we have very little area under the x plus lambda k0 squared e to the minus x squared function for the range of x values from minus infinity to minus lambda times k0. And so if that's true, then we can safely replace the lower limit of the integral. Oh, that's not right. Integral with minus infinity. Okay, I'm going to add another page. I need some more space. Okay, so what we're left with then is that this grand potential for the Roton part of the spectrum is approximately minus v over 2 pi squared kbt e to the minus delta over kbt all divided by lambda cubed. And now we have the integral from minus infinity to plus infinity of x plus lambda times k0 squared e to the minus x squared dx. So this can be evaluated. I did it in Maple, and what it came out to be is minus root pi over 2, 1 plus 2 times lambda k0 squared. And again, if lambda k0 is large, we can ignore the plus 1, and what we would get is root pi times lambda k0 squared. Okay, so we're going to get a lambda squared, and then we have a 1 over lambda cubed here, so there'll be some cancellation, and what we'll find is that our grand potential is minus v over 2. So we have a pi squared in the denominator and a root pi in the numerator, so we get pi to the 3/2 kbt e to the minus delta over kbt. We canceled 2 factors of lambda, and what I'm going to do is I'm going to put h bar squared here so we could write our k0 multiplied by h bar, so it has like momentum units. And let's just remind ourselves that 1 over lambda was equal to 2m kbt h bar squared. It's going to be important to put in that expression for lambda, because remember, what we're going to end up doing is taking temperature derivatives of this grand potential, and so we can see here that lambda has temperature inside of it. Okay, and so putting that in, then one way to express our grand potential after rearranging quantities is, you can confirm it's minus 2v h bar k0 squared root m kbt over 2 pi h bar squared to the 3/2 power e to the minus delta over kbt. And so that is our results. So what we want to do is take derivatives to get the entropy and then the contribution to the heat capacity. So the entropy is a temperature derivative of the grand potential. And if you evaluate that derivative, what you'll find is 2v h bar k0 squared root m kbt times kb e to the minus delta over kbt, all divided by 2 pi to the 3/2 h bar cubed. Right, so it's a complicated function and it's not done yet. It all gets multiplied by a term that is proportional to 1 over t and a term that's constant. Okay, and then what we're going to have to do is to find the, here, let's put subscript r. So this is the Roton contribution to the entropy, and this is the Roton contribution to the heat capacity. Now we're going to have to take another derivative, this time a temperature derivative of the entropy, and then multiplied by T. And you can see it's complicated because we have temperature here and here and here, and so we have to use product rule and chain rule a bunch of times. I'll leave it to you to confirm that the result is 2v h bar k0 squared root m kbt times kb e to the minus delta over kbt. That's all divided by the same set of constants in the denominator. And now we get delta over kbt squared plus delta over kbt plus a 3/4. And so there it is. That's the result. I'm going to show you some measurements of the excitation spectrum of liquid helium. And what those measurements were used to do was to determine some of the values of these constants. Remember, I said the adjustable parameters that we're going to have in our model are K0, the location of the minimum of the Roton spectrum, delta, the minimum energy needed to access the Roton states, and then there was this effective mass, capital M. So these parameters have been determined experimentally, and so for Rotons, let's say for Roton states in superfluid helium-4, K0 is 19.2 times 10 to the 9 inverse meters. M turns out to be about 0.16 times the mass of a helium atom. And so that's about 1.07 times 10 to the minus 27 kilograms. And delta, I just have to look up here for a second. Delta in temperature units, or delta over kBT, comes out to be about 8.65 Kelvin. Okay, and so now we're considering the temperature range that's kind of in and around 1 Kelvin, like less than a Kelvin. And so this delta over kBT over kBT for our temperature ranges is going to be large, and that's one of the approximations that we made. So just remember, we had this quantity 1 over lambda was equal to 2m kBT over h bar squared. And so what we could do is, for a particular temperature, we can now, since we know the value of big M, we could estimate lambda, and in particular, what we could do is we could estimate K0 times lambda, which we said was going to be a large number, and it comes out to be, for appropriate temperatures, somewhere around 11 or 12. And that's big enough compared to 1 that we were able to replace the lower limit of that integral with infinity. And so it's a large enough number that we don't lose much when we do that integral, or we don't pick up extra area when we do that integral by expanding the lower limit. Okay, so what we could do now is we could start to look at these results when we make the plots. And so here is the phonon contribution that we saw before, and that's the t cubed contribution. And here is the Roton contribution. And you can see, below about 0.5 or 0.6 Kelvin, it really makes almost no contribution at all to the total specific heat. And so, in fact, it only becomes significant above about 0.6 Kelvin, and that's when you start to access the Roton states that are at a minimum energy of this delta. The black line is the sum of both contributions, and you can see it's pretty good. It's pretty good match to the experimental data. There are some deviations above 1 Kelvin, and so that gets exaggerated when you go on a linear scale. And so here's the linear scale, and so it's still not perfect. There are some differences between the theoretical line and the experimental data at temperatures around 1.5 Kelvin, but it gives some pretty strong evidence that the calculation based on the dispersion relation predicted by Landau has some really serious merit. And in fact, what you can do is you can actually measure the excitation spectrum or the dispersion relation using neutron scattering. And so these are experimental results of the excitation spectrum of superfluid helium from neutron scattering, and you can clearly see the phonon part of the excitation spectrum and the Roton part of the excitation spectrum in the data. And here is the speed of sound based on the results from the neutron experiments, and then here are the parameters that we used for the Roton spectrum. Here, this is the momentum K0, and mu r is what we call that big M, so it's the effective mass. And so that's where those numbers came from. All right, good. So I'm going to stop there for today, and I will talk to you next time. Thank you very much.